All right. Good morning, everybody. Last week of lectures. And in group theory, we talked about, so far, we talked about group actions. And we talked about group homomorphisms. And one fundamental result relating them is that to every group action, so let G be a group acting on a set S, there is an associated homomorphism from G into the group of bijections of S. There is a homomorphism which I denote by rho from G into the group of permutations of S, which we denote as sim S, defined by rho of G should be some bijection of S. And what should it be? Well, it simply should be what G does on X for any X in S. Conversely, given any group homomorphism rho as above, there is an associated group action of G on S. And these correspondences are inverses of each other. These correspondences are inverses of each other. Okay, so I spelled it out because I'm going to call this a theorem. Yeah. All right. So it's quite a long-winded statement, but what it says is that we can think of an action as a homomorphism if it suits us, or conversely, if you have a homomorphism of a group into the symmetric group, we can think of that as an action. And there's not really very much meat in this theorem. The proof, as you're going to see, is quite easy. It follows almost from the definitions. It's more about language, more about the way we think of groups and actions. Sometimes it's better to think of a homomorphism. Sometimes it will be better to think of an action. And I'll give an illustration shortly as an application of this result. But let me prove it first, because the proof is really quick. Proof. Okay. Suppose that we have an action. So we have to prove two things, yeah? Suppose first we have an action. G acts on a set S. And rho, define rho as above. As above. Okay. Well, first of all, it's not clear, is this this map rho, is it a bijection of S? So is rho indeed a bijection? Indeed a bijection of S for any G in G? Question mark. Yeah. Oh, is it? Well, I claim that it is because it has an inverse. And the inverse is rho of G inverse. Note that if I compose rho of G with rho of G inverse and act on an element X, by definition, this is G acting on G inverse acting on X. But by the definition of an action, this is the action of G inverse dot X, identity acting on X, which is X for any X in S. Hence, rho G composed with rho G inverse is the identity on S, and similarly, the other way is similar, and similarly, if I compose rho of G inverse with rho of G, also I'm going to get the identity on S by exactly the same argument as above, interchanging the rows of G inverse, and this shows that rho of G has inverse map namely rho of G inverse, and hence it's a bijection of S. Okay? So indeed, this definition sends the elements of G into the bijection of S. And is this a homomorphism? Now, rho is a homomorphism provided for homomorphism we need rho of G1, G2 to be the composition of rho of G1 with the rho of G2. Yeah. Remember the group operation on the group of bijections is composition for any G1 and G2 in G. Okay, is this true? So let's test it by taking an element from S and apply these maps on S. Now the left hand side is rho G1, G2 applied on X is G1, G2 dot X. Yeah. Right hand side is rho of G1 composed with rho of G2 applied on X. By definition, this is we do G2 dot X and then we do G1. Yeah. But they're the same because this is a group action. Now, G1, G2 dot X is equal to G1 dot G2 dot X. Since this is a group action, acts on S and hence left hand side is equal to the right hand side for any X in S, and so rho is a homomorphism. In fact, what this shows is that rho is a homomorphism if and only if we have this identity, right? So, in fact, if I call this star star, and if I call this statement star, in fact, this shows the star is equivalent to double star, and hence we reduce the converse, and hence conversely, given any rho from G into sim S, which is a homomorphism, we have an action, a well-defined action, of G on S by simply reversing the definition. We define G dot X to be a row of G on X. Okay. For any G in G and any X in S. Right? Well, this shows that we satisfy the second axiom of action, and the first condition of an action is that the identity on X should be X. Well, by definition, this is a row of E applied on X in that case. But a homomorphism sends identity of the group to the identity of the image, which is the identity map on S. So this is the identity map on S applied on X, which is X itself, and hence EX is equal to X for any X in S as required as well. Right. Okay. So this proves that the converse part of the theorem, that given any homomorphism, we can define an action of the group by what this homomorphism does on the group elements, on the elements of S. Okay. So I hope I've convinced you that the result I stated is proved, and also it's, as you can see, it's not very deep. Yeah, in some sense, we're just rewriting the same thing in different forms. Yeah, this is just a matter of notation. This is equivalent to the homomorphism, just a matter of notation. Yeah. So now, why is this a good statement to have? I'll scroll back now to the statement of the theorem. Okay. Let's apply it immediately. And at the beginning of the course last term, I said that I mentioned Cayley's theorem, that every finite group, in fact, is isomorphic to a subgroup of the symmetric group. So let's prove this. Theorem is known as Cayley's theorem. It's more concrete to state for finite groups first, so let G be a finite group. Then G is isomorphic to a subgroup of the symmetric group Sn for some n. Okay. If G is infinite, we can only deduce that in fact, if G is any group, finite or infinite, G is isomorphic to a subgroup of sim of G. So the more general statement is this, that any group is isomorphic to a subgroup of the bijections of the group itself. Now, if the group is infinite, the problem is that this group is very big. So if you have an infinite set, the set of bijections between it is uncountable at the very least, as it's easy to see. So for infinite sets, the group of bijections between themselves is just too big to study. It's kind of not very useful. This is rarely used if the group is infinite. Okay, but if it's finite, then of course we are talking about finite symmetric groups. Okay, so let's prove it. Okay, well, considering what we said earlier here, we we want to think of an action of the group which sends and consider the resulting homomorphism that will send the group into the group of bijections of a finite set, and we want to make sure that this row is injective. And how do we do that? Well, as I said earlier, when you know nothing about the group, the natural thing to study is basically the action of the group on itself. There's really nothing more you can do. You don't know anything about the group. Yeah. So what we're going to do is, we already have seen this. Consider the action of G on itself by left multiplication, i.e. G acts on X by Gx, the product of G and X, for any X in S, go to G. We already seen this as an example, that this is indeed an action. Okay, and define the associated row. This gives a homomorphism row from G into sim of G, defined by, well, the definition is there. Row of G applied on X is Gx for any G and X in G. Okay, we already know this is a homomorphism because this is what we proved earlier. The only thing remaining to check is that this is injective homomorphism. We need to prove that rho is injective, i.e. the kernel of rho is the identity of G. In that case, by the isomorphism theorem, we know that G, the image of G, well, rho of G, let me call it rho of G. This is the image of rho. This is isomorphic to G modulo the kernel of rho, which is just G. Yeah. And hence, G is isomorphic to a subgroup of the group of permutations of G. Okay. All right. So this is what we need to check. The kernel of rho is the identity. Well, let's check it. Suppose I take an element in the kernel of rho. What does this mean? It means that rho of G is the identity on S, the identity on G, i.e. Okay. i.e. in other words, G multiplied with X. So rho of G applied on X must be X for any X in G, right? That means to be identity, but this is just Gx, right? So we need that Gx is equal to X for any X in G. Well, you can just cancel X, or you can just take X to be the identity and deduce that G is the identity, right? Hence, kernel of rho is the identity only, and rho is injective as claimed. As claimed. Right. And this proves everything, yeah? So if G is finite, we let n be the size of G, and hence we have shown that G is isomorphic to a subgroup of sim G, which is the same as Sn, right? The permutations on n elements is just the symmetric group Sn, and this proves Cayley's theorem. Yeah. All right. And this connection, as you see, the main thing we really had to prove is that the kernel of rho is the identity, and such actions have are important. They have name. They have to deserve a name of their own. Such actions are called faithful actions. Definition: an action of a group G on a set S is said to be faithful if the kernel of the associated homomorphism is the identity, or equivalently, the only element of G which does nothing on the elements of S is the identity. Or equivalently, if G is an element of G such that G dot X is equal to X for any X in S, then this G must be the identity. All right. So it's just a definition which says faithful actions are the ones that actually see the action sees all the elements of the group. Yeah. If you have a non-trivial element of the group, non-identity element of the group, then it must move some x. Yeah. There will be gx will not be equal to x for some x in x. Okay. And what we've proved above in the proof of Cayley's theorem is that the action of G on itself is a faithful action. Okay. All right. Okay, so now we can apply this philosophy to identify the group of rotations of the regular polyhedra. So recall that the definition that G C, G T, G I, G O, and G D are the group of rotations, the groups of rotational symmetries of the cube, regular tetrahedron, icosahedron, octahedron, and dodecahedron respectively. And I can put now what we're going to do next in one big theorem, which we can state quickly as follows. The group of rotation of a regular tetrahedron is isomorphic to A4. The group of rotations of the cube is the same as the group of rotations of an octahedron, is isomorphic to S4. And finally, the group of rotations of the icosahedron is exactly the same as the group of rotations of a dodecahedron, if you identify the dual polyhedra, and it's isomorphic to the alternating group A5. Okay. We've already computed the sizes of these groups. Yeah. Here the size of the group is 12. Here it's 24, and here it's 60. Yeah. These are sizes. We already did this with the orbit stabilizer theorem. So certainly these numbers, the sizes of the groups match up. But we also, with this statement, we actually know them as groups. Okay. Right. Well, let's spend some time proving these results. This is easy. This is slightly more complicated, and this is a bit more complicated. It's a nice exercise we're going to do for maybe also some time of the next lecture. I won't have time to explain this in full today. All right, A4. Well, this is talking about, so this theorem is talking about a group isomorphic to some permutations. And we already have the tool for that. Yeah, we have to use this theorem that we have to find an action that's such that the associated homomorphism is faithful. The associated action is faithful. The homomorphism is injective, and the image is precisely the group that we want. Okay, A4. How do we get A4? Well, we have to act on 4 things, and we have the group of the tetrahedral group. Right here is a tetrahedron, yeah, with its group acting on it. What should we act on? Well, obviously we have to act on the vertices. Yeah, there are 4 vertices. Let's act on them. So all right. Proof. First, GT acts on the set S of the 4 vertices of the tetrahedron. Vertices of T. Okay. And consider the associated homomorphism. Consider the associated homomorphism rho from G into sim of these vertices, which is just S4, right? Is this action faithful? Well, what does it mean to be faithful? It means if I have a rotation which fixes all the vertices of the tetrahedron, is that rotation the identity? And the answer is yes, yeah, because if it fixes 4 vectors, any linear transformation that fixes 4 vectors, at least 2 of them are linearly independent, it will be the identity linear transformation, yeah. So the action is faithful, yeah. Action is faithful. So rho is injective. Then G is isomorphic to the image of rho, which is a group of size 12. In S4. And from here on, we can either say, we can show that the only group of size 12 in S4 is A4. That would be one approach. But we don't really have to go to such length, because we can immediately see that all the possible symmetries of a tetrahedron, there are only 12 of them, and you have, for example, the rotations of order 3 through a vertex and the midpoint of a face. So if I have this this symmetry theta along the axis that goes through V1 and the midpoint here of the opposite face, then a rho of theta will correspond to the permutation, to the cyclic permutation of these vertices, right? It will be the cyclic permutation V2 goes to V3, V4, or its inverse. Yeah. So it's a 3-cycle in any case. So even permutation. And the other possibility is if we act with a rotation with an axis through the midpoints of two opposing edges, and then that will be rho of theta prime. We'll just be swapping a pair of vertices, right? We're swapping V1, V2, and V3, V4. Again, even permutation. So image of rho is exactly A4. Yeah, we can get all the elements of A4. It is specific. We can just list all the symmetries of the tetrahedron. We get all the even permutation on the 4 vertices, so the image of rho is A4, nothing else. Okay, this proves the first part, the easy part. Now about the cube, part 2. Well, as I said, I'm not even going to consider the regular octahedron because it's a dual polyhedra to the cube, so they have the same rotational group. So I'm just going to consider the rotations of the cube. We know there are 24 of them. And we have to act now on 4 things, yeah, because we want the homomorphism into S4. If we consider just the action on the vertices, that will not be the right thing to do because there are 8 vertices of the cube. Indeed, we will get a homomorphism of the rotation group into S8, and it will be injective. This will be, again, a faithful action, so our group will be isomorphic to a subgroup of S8, but it will not be all of S8. It will be a subgroup of size 24 inside S8, and we will have trouble identifying which that is. Yeah. So we need an action on 4 things. And the natural thing to take here is the action on the diagonals of the cube, the main diagonals here that I've listed by D1, D2, D3, and D4. And I've drawn just one of them. From V2 to V8, one of the main diagonals. Okay? And there are 4 of them. So we consider the action of the group of rotations of the cube on the 4 main diagonals. D1, D4 of the cube. Okay. And now the question is this action faithful, right? Okay, this is the thing we need to check, and the answer here will be yes. And let's prove it. Suppose that I have an element, a rotation of the cube, which fixes all the diagonals. Di sends Di to Di for I 1, 2, 3, 4. And I claim that G is the identity. Okay. I mean, at this point, the things are so concrete that one can argue in many different ways. But intuitively, if you think about it, a linear transformation which fixes 4 of these diagonals, what does it mean for linear transformation to fix a line through the origin? Well, it means it must have an eigen, this must be an eigenspace, right? And since we have at least 2 diagonals, linearly independent, our linear transformation has 2 eigenspaces, linearly independent, so it's diagonizable. The eigenvalues, because it's orthogonal, must be plus or minus 1, right? Sorry, 3. I need 3 eigenspaces. Yeah, 3 linearly independent eigenspaces, 3 linearly independent diagonals. So our linear transformation must be diagonizable with eigenvalues plus minus 1. But if it's not the identity or minus the identity, it will not be able to fix the 4th diagonal just by inspection. So that would be one way to do it, using linear transformations, or we can just use it as I'm going to write up now, just by considering several cases, right? So we know that G sends the first diagonal v1 v7 to v1 v7. So therefore G of v1 is either 1 of v1 or v7, right? Okay, so suppose that G actually sends v1 to v1. So suppose that G fixes this vertex, right? This is fixed. But now let's look at the v2 v8 diagonal. G on v2 must be 1 from v2 or v8, right? Because because v2 v8 diagonal is being fixed, so this must be one of the 2 vertices. Now v2 is of distance 1, is 1 edge away. So if the length of the cube is say 1, since G is orthogonal, rotations are orthogonal maps, the distance from v1 to v2 must be the same. Maybe I call it distance is equal to the distance from v1 to v2, yeah? But this is just v1 because we're fixing it. So therefore G of v2 must be a neighbor, a neighboring vertex. Vertex of v1, yeah? So it's one of the 3 neighboring vertices, v2, v4, or v5. But it must be either v2 or v8. By this thing, and v8 is not a neighbor, right? So these 2 together imply that actually G fixes v2 as well. Okay. Okay, but now we can continue, right? We can now move to a neighbor. So I mean, by similar argument, it fixes all the neighbors of v1 similarly. G fixes all neighbors of v1, and so G is the identity, right? The only rotation that fixes these these 4 vertices is the identity. So we are good here. That proves the claim in that case. And case 2 was suppose now that G swaps V1 and V7. G sends V1 to V7, and of course this means that G must send V7 to V1, right? So G flips this diagonal. But then again we look at the neighbor. So again G sends the neighboring vertex V2 must be a neighboring vertex neighbor vertex to its image GV1 to neighbor V7. So G must send some V2 to a neighbor of V7, but at the same time, because it preserves the diagonal D2, G of V2 must be 1 from either V2 or V8, right? And the only thing that is a neighbor, the only one of the two that is a neighbor of V7 is V8. Yeah? So from here, from these two, the conclusion is that G sends V2 to also to its opposing vertex V8. And similarly, we deduce that G sends V5 to the opposing vertex V3, and G sends the other neighbor V4 to the opposing vertex V6. But then G is the minus the identity linear operation, right? It kind of sends each vertex to its opposing vertex, but this is not a rotation. So there is no such rotation that does this. Okay. Okay, so this proves the claim. Claim is proved. Action is faithful. Therefore, the group of rotations of the cube is isomorphic to the image of rho, which is a subgroup of S4. But now comparing sizes, however, the size of the rotation group, we know it's 24. That will be the size of the image of rho as well. Hence, rho is injective, rho is surjective, and G rotation groups of the cube is isomorphic to S4. Just by knowing sizes of these groups, we can deduce, we get all the possible bijections between the diagonals. Yeah. And we can also specifically list all the elements of the rotation groups of the cube, and I already did that in the previous lecture when I was doing this exercise with counting how many ways are there to paint the vertices in 2 colors. I listed all the elements of the cube, so I'm not going to do it again. But you can actually do you can go through the list and see how they do, what they act on the diagonal, and you can actually get an explicit map rho from the rotations of the cube to permutations. Yeah. Okay. So now we are done with 1 and 2, and it's a lot more interesting what happens for the icosahedral group A5. We certainly know that they have the same they have the same size. Yeah, we computed the number of rotations of the icosahedron using the orbit stabilizer theorem. It's 60, exactly the same number as elements of A5. So the question is, how do we prove the isomorphism? I'm going to show two different ways to do that. Let me first mention a helpful result. Let me just state it as a proposition. It's a useful result to have. Let H be a subgroup of index 2 in a group G. Then the claim is that the square of every element belongs to H for G in G. Okay, let's prove it. Well, we know that, so if G is already in H, we are done, yeah? Then, of course, G squared is in H, and we are done. And if G is not in H, then we have the decomposition into cosets. G is equal to the union of H and GH as cosets, right? The disjoint union of two cosets, because the index is 2, right? That's what it means, that they're just two cosets. But then what are the possibilities for G squared? Then look at G squared. If G squared is not in H, then G squared must be in GH, right? Because that's the other possibility. But this means that G squared must be equal to G times something from H, G times H, for some H in H. But now we can cancel G and deduce that G is equal to H is in H, which is not this case, not true. Yeah, because we assume G not. Okay, so this proves that hence G squared must be in H as claimed. Stop. Proved. Okay? So that's more generally, you can prove that similar argument can prove that if you have a subgroup of index, a normal subgroup of index n in a group must contain all the nth powers of the element of the group. As a corollary, I'll just quickly spell something. The only subgroup of index 2 in S5 is A5. Okay? And the proof is that every even permutation is a square of something. Yeah. So, for example, look at this. ABC is actually the square of ACB, right? ABCD. This is the square of ACBD squared. Yeah. ABCDE. The 5 cycle will be the square of its third power. Yeah. Yeah. So yeah. So you can get all the elements, all even permutations as squares of permutations, and that proves the claim. Okay. And since I'm out of time now, I'll just give now a quick version of the first proof why the isometries of the rotations of the icosahedron are isomorphic to A5, we need to make the rotations of the icosahedron act on 5 things. Yeah, but if you look at an icosahedron, it's not easy to find something divisible by 5 in it. And the only thing that actually makes sense is to look at the number of faces, the number of triangles here, and there are 20 of them, and 20 is divisible by 5. So what you can do, you can label the faces by numbers from 0 to 4, so with 5 colors, such that the faces of the same color are of distance 3 from each other. It's the way I have drawn it here. So for example, 0 is this 0, 0 here, 0 here, and the whole here. Yeah? Okay. And in this way, we have 5 colors, each of them labeling exactly 4 faces, defined in a way that is distance defined. So any rotation must actually permute these colors. Yeah. So we consider now the action of the rotation group on these colors, and we have to basically prove that this is a faithful action, which you can do by examining what happens if you fix one color and so on. It's it's a bit of little case-by-case analysis, but it's doable. And then once we do that, we are done, because now if you have a faithful action of the group on 5 things, we have therefore the group isomorphic to a subgroup of S5. That subgroup has size 60, because we know the size of the icosahedral group is 60. So we have a subgroup of index 2 in S5, and by this corollary, we know it's A5. So this is one way to prove that the icosahedral group is isomorphic to A5. This is a short way, but it kind of has a little bit of gaps in the argument, as I said. And in my next lecture, I'll give a different proof, which uses a lot of the tools that we've already developed. It's a bit longer proof, but it's also good in the sense it introduces more applications of what we have done so far. Okay? To be continued next time. Thank you.